So from chapters 4 and 5, you would still need to know density function, the probability mass function, and the means and variances of the distribution.
You said the density function, probability mass functions, mean and variance?
Mean and variance, right, yeah. So we started with joint distributions, that's chapter 6. If x and y are discrete random variables, I will talk about the joint probability mass function, and that's just the probability that x takes the value little x, and x takes the value little x, and y takes the value little y. To get your individual probability mass functions, we will call them marginal probability mass function. If I give you the joint probability mass function, ask you to find the marginal probability mass function, what you do is, if it's the probability mass function of x at the point x, keep x fixed, sum over all your y's. So this is just the probability x, the value little x. So it's x can take the value little x, and you sum over all the possibilities of what values y can take. For the continuous case, we talk about joint density functions. Joint probability mass function, and here we have joint probability density function. This clearly I can't define this directly in terms of probability, so joint density function is basically a function of two random variables that's non-negative, and it integrates out to 1. So it satisfies those properties. And its relation to probability is the following. The probability that this pair random of xy lies in some A, clearly A is now a subset of R squared. So it has this set of all tuples, is a double integral over this over the region A of this density function. So it's extending the idea of density function from a single random variable to two random variables. So probability that x and y lie in some region. So supposing the region A is x is between 1 and 2, and y is between 2 and 3, okay? And I'm interested that x and y lie in this region A, that is, where x is between 1 and 2 and y is between 1 and 3, I have my density function defined over R2, and what I would do is I would integrate over this region A. So this is just calculus. So the probability that xy lies in some region A is just the integral of your density function, the joint density function, over the region A. So the only tricky thing in these problems are trying to figure out exactly what this region A is. Okay, so what region to integrate over. Okay, so that's just a quick review of what we've done so far. To start with section 6.2. All this is section 6.1. Today we're getting started with section 6.2. Independent random variables. So what do I mean by independence when it comes to random variables? When do I say two random variables x and y are independent? So here's the definition. Random variables x and y are independent if for all choices of sets A and B, the probability that x is in A and y is in B is just the product of these individual probabilities. Probability that x is in A times the probability that y is in B. So knowing what you know about independent events, this should be a natural definition for independence of random variables. So random variables x and y are independent if these two events, x lying in the set A and y lying in the set B, are independent events for any sets A and B. So this is the general definition of independence. Now it's not easy to prove independence using this definition because you're not going to check this condition for all possible sets A and B, right? So here are equivalent conditions or definitions. So in the discrete case, this is equivalent to probability that x takes a specific value A and y takes a value B. Or, in other words, well, this has to hold for all AB, for all numbers AB. So you don't have to check that they're in some set. Just check that in the discrete case, the random variables can take specific values with some positive probability, right? So you check it for all possible values x can take and y can take. So this is equivalent to checking that this is just the joint probability mass function at the point AB. If the joint probability mass function is just the product of the marginal probability mass functions, then we say they are independent. So in the discrete case, to check for independence, all you need to do is check that the joint probability mass function equals the product of the probability mass of the marginal probability mass functions. You need to check this for all possible values A, B. To disprove this, of course, all you need to do is find a pair of values A and B such that this does not hold. So it's easier to disprove. In the continuous case, any guesses? Check that the joint density function is just the product of the individual density function. Joint density function is the product of the marginal density functions for all x. So this is the condition to check for independence. So let's do some problems based on independence. Ability P that x and y are x and y independent. Okay. Intuitively, you can already guess that they shouldn't be independent if I know that x is 1. X is number of heads. That means a head is turned up. That means y has to be 0. Okay, so we already know that they shouldn't be independent, but don't always rely on intuition. Just check the condition. Okay. So the condition for the discrete case is this. So for the discrete case, if they're independent, this will hold. If they're not independent, this will not be true for some pair of values A and B. So first of all, what is x? X is a random variable that can take the value 0 or 1, because either you can have no heads or you can have one head in one coin toss. Y is again 0 or 1, either you can have no tails or one tail, depending on, it's just the outcome of one coin toss. Right? Okay. We already suspect they're not independent, so we just need to disprove this for some pair. Well, we already know this. What's the probability, the joint probability, that both x and y take the value 1? That is, you get one head and you get one tail. That's impossible, right? So that's a 0. Calculate probability x equals 1, multiplied with the probability y equals 1. What do you get?
Oh, what? Oh. Quarter.
Yeah. The probability that x equals 1 is the probability of getting tails, right? And so that's 1/2. Multiply with probability y equals 1, sorry, x equals 1 is probability of getting heads. Probability y equals 1 is probability of getting tails, which is also 1/2. So this is 1/4. So this product is 1/4, but this is 0. So this is not equal to this.
And there's no need to keep checking other...
Yeah, if we just, so if they were independent, this would be true for all A and B.
Right.
So if you show that it's not true for one of them, that means it's not independent. X and Y are dependent. So if they're not independent, we say they're dependent. So always check for something like this. Check that it does not hold for one pair of values.
Now, say they were independent,
Then
then we'd have to check when x is 0 and y is 1.
yes.
And then when y is 0 and x is 1.
Yeah, and when both are 0.
And when both are 0. Okay.
So you have to check for all possible x and y values.
Okay.
All the one with density functions. Supposing I give you, so this is not so obvious if they're independent or not. The joint probability density function of two random variables, x and y, is given by this. The question is, are x and y independent? So if they were independent, then the joint density would be the product of the marginal. First step is you have to first calculate your marginal probability density functions. So you first calculate those, and then we will check if that condition holds. So you're given the joint density function. From the joint density function, how do you calculate your marginal density functions? So the marginal density function for x, you integrate out your y. So first calculate your marginal density function. So fx of x so you keep x fixed at this, and you integrate out. So if I did an fx of a, it would be fxy a comma y. So what is your joint density function? Your y takes values from 0 to 1, and so this is just going to be 0 to 1 plus x plus y. So this is so 1 plus x times y plus 2 times 1, so it's 1.5, 1 plus x, 1 plus 1 squared, 2 minus, this value is 0, is just 0, so you have 1 plus x plus 1/2, so 1 plus 1/2, 3/2, so 1/2 x plus 3/2. Similarly, calculate fy of y.
That's the number from negative infinity to 0.
No, this is not negative infinity to 0. It's negative infinity to plus infinity, but this function is this only when y is 0 to 1. So I'm just integrating from 0 to 1. Let's look at your density function formula. It's non-zero only when y is between 0 and 1.
What does it say?
Here?
I just need glasses. No, it's the coefficient of y right there where your finger is.
Here,
Yeah.
here,
No, right
Oh,
up
here.
there. Yeah.
1 plus x.
Oh, 1 plus x, so it's 15.
Okay. So 1 plus x y plus y squared over 2. Oh, this is 2. This is 1 over 2 here.
No. I got it.
Okay.
Thank you.
All right. So let's just do integration. Density function for y, you can integrate out your x, but you should get the same formula, but in y, because this is, if you look at it, it's symmetric in x and y. You would get this to be 1/2 y plus 3/2. So the question is for all x, y, that is, this function, and you check that this is equal to, we get this for all. So that's the question. Well, let's just check it maybe at a couple of points. So it doesn't look like it is going to be equal. I'm just looking at the functional form. I mean, you're going to have x, y terms and x multiplied by y. But it's best to just check a couple of points. So what values, so this is valid in this region, right? So take x equals 1/4 and y equals 1/4. What do you get? X equals 1/4. The left-hand side is, you get x plus y over 2.
3/4.
Is equal to, what do you get? 1/4 is 1/4, that's 1/2. So that's 3. What about 4 times fy of 1/4? 1/4 quarter plus, let me say 6/4.
49/16.
Quarter plus 6/4. So 7 out of 4. 7 out of 4. So 7 square 4 cubed. Which is clearly not 3 or 4 because factor 7 is not here. All right. Okay. Is that right? Yeah. Okay. So you see that that's not true.
So they're dependent.
So they're dependent. Now, if you had checked x equals 1/2, y equals 1/2, you would have got them to be equal. So if you get them to be equal, that's not, you've just checked at one point. So if it's equal at one point, it doesn't mean independence. It needs to be equal everywhere for all x and y's to be independent. So if you get it equal, you have to check another point. Okay. So keep checking until you can prove it's not equal. Or if you can prove that, oh, this functional form is definitely always equal to this. All right. So
How would you prove that they're always equal though? Because you would have to check.
Do the distribution.
you multiply this out and look at the function that you
Oh,
get.
just multiply it out.
Yeah.
Okay, and if
So
the
if you
functions are equal, then you can.
Yeah.
Okay.
You see when you multiply this out, you get a term which is x times y plus 9. Yes.
Which is 9.
Yeah.
Okay.
So what you could do is say set them equal to each other, and then try and simplify and get some contradiction. So that's
Okay.
Okay, the bottom line here is 1/4, 1/4.
yeah, 1/4, 1/4. I mean, I just said plug in the point 1/4, 1/4. Right.
So those are 1/4 across the board? 1/4 FY, 1/4.
Yes, fx 1/4, fy 1/4.
Okay.
Right.
After that question mark, it says 4, is that 0 less than x?
Yeah, 0 less than x,
Y
so
less
x and
than
y are between 0 and 1.
Oh, I got it.
Right?
Okay,
Basically, this
I
condition.
got it.
here's,
Bless you.
let's see. Here's another example. The joint probability density function of x and y is given by this. Zero less than equal to x.
I'm sorry, one more thing.
Yeah.
So we're saying that this last probably not independent.
Yeah, it's
Okay.
yeah, right, yeah. Independent. Because at x and y equals 1/4 each, you get this not equal to this product. So you can go ahead and do the same calculations. Okay. That first calculate the marginal probability probability density function fx of x, probability density function fy of y, okay, and then check if the product equals this. But there is actually an easier way of thinking about this. What are the possible values your random variable x can take?
0 to infinity?
0 to infinity. What are the possible values y can take? Also 0 to infinity, right?
But it has to be less than whatever the x is, right?
Or
Or can it be less than or equal to?
The thing is, simultaneously, you cannot have, when x is 1, y cannot be 1/2.
Okay.
But if I just ask you what's the but y does have a probability of taking the value 1/2. But that would be when x is 1/4, say.
Okay.
So y, if I calculate fx of x, this will be non-zero for x, there's a 0, and fy of y for y.
Okay.
Because, so that means that x can take all values that are greater than 0, y can take all values that are greater than 0.
Okay.
Because I can take y, so y can take values that are very small and close to 0, but as long as x is less than that too. So
As long
for-
as x
so,
is closer
yeah,
to 0.
right, yeah.
Okay.
So if I ask what's the probability that y equals 0.002, that still has some positive probability. It can't
Right.
take those values. So I would integrate this function over all x's going from 0 to 0.002.
002. Okay.
So this is obvious now that x and y can take all positive values. What about this? What is the value of this? That is x, in terms of probability, is like saying, can x take a value close to 2?
0.
This is 0, right? Because this function is this only when y is greater than x, and is 0 elsewhere. So when y is less than x. So this is 0. But I know fx of 2 is always positive. Okay? Because it'll take some positive value, because it will be the integral of this over some region. And fy of 1 is also some positive value. If I just look at the probability of y taking the value 1. So now we have these cannot be equal. So y on its own can take values between 0 to infinity if I don't look at what x is also taking. If I just ask you what's the probability that y takes a value, I can calculate that. That depends on the density function for y.
You don't know it's 2.
Listen. 2. Okay, so what I've written is f of xy at the point 2, 1 is 0. This is not equal to fx of 2 times Fy of 1.
This equals 0, you said?
This equals 0, but this product does not equal 0.
You know that fx of 2 is not equal to 0. How do we calculate fx of 2? We would integrate
Yeah, so
e to the negative y with respect to x from 0 to infinity.
y.
Oh,
This would be
negative infinity to infinity?
negative to infinity. So now if I plug in the function, it's 0 in some region, right? So it's non-zero, and it's e to the negative y. So that's the definition, right? Okay. Now plug in fx of 2y. When y is less than 2, fx of 2y is 0. Right? So it's e to the negative y only when y is greater than 2. So this is always going to be something positive. E to the negative y is positive, strictly positive, and I'm integrating it over something. So you can find what it is. Negative y.
Okay.
0. So e to the negative 2. So that's the value of fx of 2. Okay, what's the value of fy of 1? I look at the joint density function, I keep my y value fixed at 1, and I integrate out all my x's. This function, what does it look like? It is non-zero and takes the value e to the negative y, but the y here is 1, so it takes the value e to the negative 1, as long as x is less than y. So x goes from 0 to 2. So it's just e to the negative 1.
So to get the marginal probability density function of x, we integrate with respect to y.
No, say that again?
To get the marginal
Density function for
density
x.
function for x, we integrate with respect to y.
Y, yeah, you integrate out your y.
Oh.
So I want fx at the point 2, so it's f of x, fix your x value at 2, integrate out your y.
Oh.
Okay. So clearly your answer should not depend on y anymore. Okay. It's going to be y. So this joint density is 0 at the point 2, 1, but that's not equal to fx of 2 times fy of 1, because what was fx of 2? E to the negative 2 times e to the negative 1. All right, so in fact, anytime your density function, it's defined over some region like this, where you already see there's a dependence between x and y. So the only place where it's not the region is not dependent is if it's a rectangular region. That is, if I say, if instead of this, I had, as long as a was in some interval, and x was in some interval and y was in some interval, this is a rectangular region, right, for x and y. So if my function is defined so that it's non-zero over a rectangular region, okay, then it could be independent or not independent. But if it's defined in any region other than this, that means a region like this, where there's some dependence between x and y, then they're always going to be dependent. Because you see that this is obviously true that if you took a y value less than x, then that density function is 0, but you know y can take every value between 0 to infinity with some positive probability. X can take every value between 0 to infinity with some positive probability. So you always have, this is positive, but this is 0, because it violates this condition. Okay, someone tell me the time is, I don't know, once again. 25? Okay, we still have stuff to do. We still have stuff to do.
Oh, I think you read the clock wrong. It's 5:45.
That's not.
We don't have time.
No. Stuff to do.
Are you going to assign homework for Wednesday, or is last week's? due?
No, there's no homework for Wednesday.
So we're doing that.
And our next one will be due the following Wednesday.
Yes. So homework on this material would be due next week. So important things to note. So keeping this example in mind, in general, if the set of values where the joint density is positive is not a rectangle. X and Y are not independent. So if the region is not a rectangle, it's not independent. Let's see, what does this region look like? So what is this region over which my density function is not zero? X is, that's not y. So this is the line y equals x. So that's axis.
So it's the shaded region below it.
Is the region
Above
y
it?
has to be above x.
Oh.
Yeah, we're talking about that.
Yes. So this is the line y equals x, and I want the region y greater than x. So at any point x here, y has to be greater than this point. So this is the region, so this is this region. So your density function is e to the negative y over this region, and it's zero elsewhere. All right, and clearly this region is not rectangular. So it's you know already by this remark that it's not independent. Take one more example. Now what if I gave you, let me give you another example. So you know the general method for checking if two random variables are independent or not, if they're continuous. If I give you the joint density, you find the marginal densities. The way you find them is you integrate out your, if you want to find the marginal density for x, you integrate out your y. To find the marginal density of y, you integrate out your x. And then check that the joint density is equal to or not equal to the product of its marginal density. Supposing I give you an example where the joint density function is sine x, cosine x, e to the sine x minus y over 2. if this region had not been a rectangle, we could have just used our mark and said that's big enough. But this is a rectangular region. The region y greater than 0 and x between the target two. So what's our region over which this is coming 0? So this is x goes from 0 to pi over 2. And y, so this is our region where it's non-zero, it's defined like this. Now, how many of you would be willing to integrate this to get Marshall density?
Thanks.
I prefer not to.
So actually, you don't have to, because there's another trick, and I'll state it as a theorem. Yeah, so no one wants to integrate this, that's okay, we will use this theorem. I'll write it as
That's
a
e
problem.
to the negative 1, or is that e minus 1?
E to the negative 3/2? Oh, this is e minus 1, yeah, e minus 1. First of all, notice that this ugly function here, it can be written in this certain way. You can club all the x terms together and multiply it with all the y terms. So let's get all the x terms together. So you get cosine x times e to the sine x. And let me take all the constants with this.
That's e to the sine x minus 1 over 2.
E to the sine x, yeah, minus y over 2, right. And then collect all your y terms. And it's e to the negative 1. So notice that this function can be written in this form. You can collect all the x terms. It can be written as a function of x times a function of y. And if your density function has this property, then it's independent. So, yeah.
Is that square root of 2 pi?
Yeah, square root of 2 pi. So whenever your joint density function can be written as a function of x times a function of y, it means it's independent. And we can prove this here. If, let's write it down as a statement, x, y can be rewritten as some function of x times some function of y, then there is a constant c, so that this would be c times this function of x. The marginal probability density function would just be some constant times that function of x, and the marginal density function of y would be 1 over c times h of y. Therefore, xy would be g of x times h of y, which is, I mean, this. The c and c would cancel out, and you get g of x times h of y, and that is just the density function. Okay, so let's do a proof of this. So, say by property, yeah.
Is this, it's what we learned in the beginning of differential equations, isn't it? Where,
Independence is something that's unique to probability. It doesn't come to anything.
it's just very similar.
It's similar to like separable. So
Right,
differential equations.
Uh-huh.
So you can separate the two and integrate them separately.
Yeah, you can set, no, what I'm saying is this is, yeah, I mean, we'll have to use that to prove this theorem, yeah. We'll be using that to prove this theorem. So, in fact, maybe then I can leave the proof to you guys, since you know how to prove it. So basically, what this theorem is saying is that if this is of the form function of x times function of y, then it can be written as the probability density function of x times the probability density function of y. So let's prove this. Okay. Oh, okay. So we'll prove the property, but first, what we can say for this example is by that property, x and y are independent. So let me do property one, by property one, x and y are independent. So on the exam, if you can prove something like this, just say that I can write it as a function of x times a function of y. Okay, so let's do the proof of that. So how do I get fx of x is just I'm integrating out my y. That's how I get that. Now, I've told you that this can be written as a product of g of x times h of y. So I replace that. Now, this is probably what you guys were talking about. Since it's a function of x independent of y, you can pull that out. G of x. So you integrated this out, this is some number. So let's, so this is equal to c times g of x, where c equals this integral. So this is a definite integral, so it's a number. Now calculate fy plot. Fy is the integral. You integrate out your x in the joint density function, keep y fixed, integrate out your x. Again, you know that this can be written as a function of x times function of y. Function of y pulled out of this integral. So this is also some constant. Let's call this constant d. This is d h of y. We also know that this is a density function, right? So it should integrate out to 1. Again, let's use the fact that we know it's a product of a function of x times a function of y. And this is probably one of the other properties. You know that you can then write it as function of g of x. I define the integral of h of y dy as c, and this as d. So this is d times c equals 1. Therefore, d equals 1 over c. So what do I have? I have that fx of x is c times some constant c times g of x, and fy of y was d times h of y, but d is 1 over c. And so if I multiply these two, I get c times g of x times 1 over c times h of y, which is g of x times h of y, which is fxy. So I proved basically this theorem. This is c times g of x, and this would be 1 over c times h of y. So this constant d that you get is 1 over c.
Is the inverse of this property true, or the converse, as in if you can't separate the variables, then it will not be independent?
Well, the definition of independence, the definition of independence is that it is going to be, this is your definition of independence, right? That is fx of x times fy of y. So it always has to be a function of x times a function of y. Right? So if you cannot do that, that means this cannot be true then. Right? Yeah. So if you cannot do that, then it cannot be true. Well, okay, no, this is not quite right. I mean, the way this could be defined. So you're saying if you are not able to factor it, the thing is, you may not be able to factor it, but yeah, if this is a definition thing, you should be able to factor it always into that thing. Yeah. The thing is, when you do factor it, you may not be able to factor it correctly into fx of x and fy of y. It will be up to some constant because you don't know. Say in that earlier example, I don't know which constant to put with the function of x and which constant to put with the function of y. Yeah. So if you're saying that it cannot be written as g of x times h of y, that means it cannot be written as fx of x times fy of y. So then, yeah. So the converse is also, if you cannot factor them, then they cannot be independent.
Would that be allowed to be used on the exam or no?
See, the thing is, you may not be able to factor them, but they still might be factorizable. Okay. So
okay, so that's not a good method.
I mean, unless it's like completely obvious that it's not factorizable, but then in that case, it's easier to just check a couple of points, right?
Right.
So then you would just do that. Don't waste time trying to see can you. If it's very easily factorizable, yes. If it's a complicated looking function, try to factorize it. Okay. But if you suspect it cannot be factored, just check points.
Just check points.
Because you might be wasting too much time trying to factorize it.
Okay.
All right. What's the time?
Time to go?
Okay. Oh, okay. Yeah, we're going to get there. One more problem in independence, let's talk about this.